Right. Okay. So we're going to be talking about 5.5, which is on solving exponential equations and also logarithmic equations. And so in the first part, we're going to be talking about solving exponential equations in particular. And then in part two, we'll talk about solving logarithmic equations. Okay. So we're just going to kind of break it up in those two pieces. Now, what is an exponential equation starting with? Well, there's multiple different types of ways that you can see what an exponential equation is, but essentially it's whenever you have an equation with an exponential variable or a variable in the exponent, okay? So what does that look like? Well, let's look at an example like 2 to the power of 3x and set that equal to 16. So your job is to solve for x. And this is an example of an exponential equation. Now, there's going to be like multiple different ways on how to solve exponential equations. And then the first one we're going to talk about is, well, the way I'll categorize them in a certain way, right? So, for instance, if we're going to solve something like 2 to the 3x equals 16, we're actually going to use the first method, which I will call type 1. All right, so type 1 is, the goal is to create the same base. Okay. So what do I mean by creating the same base? Well, on one side, we can clearly identify the base, right? 2 to the x. Well, my base here is 2. On the right side, however, I have 16. So your goal is to see if there is a common base between them. So on the left side, I have 2 to the 3x, but on the right side, I have 16. Can I rewrite 16 as a power of 2? Or in other words, a number as the base with 2 raised to something? Yes. In this case, 16 is 2 to the 4th, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So 2 to the 4th is going to equal 16. Okay, so let me continue that. So again, this is type 1. I'm creating the same base. I'm trying to create the same base on both sides, so then we can see what happens. Ready? So we have 2 to the 3x. That's going to equal 2 to the 4th. All right. Well, if I look at the exponents and the bases, right? The bases are the same. 2 to the 3x equals 2 to the 4th. Well, it's necessarily true that the exponents have to be equal to each other. In other words, 3x has to equal 4. Okay, so solving for x here, fairly simple. Just divide by 3 on both sides. So you end up with x is equal to 4/3. Okay, so if I plug that back into my original equation, 2 to the 3x equals 16, and I plug in my x value, which is 4/3, then we end up with 2 to the 3 times 4/3 equals 16. 3 times 4/3, that simplifies with the 3's canceling out, and you end up with 2 to the 4th equals 16th. No mistake there, right? So that's perfect. So that's going to be the method for solving exponential equations for we call this method we're going to call it type 1. And so again, the goal is to create the same base. Well, okay, what happens if we can't? So what happens when we can't find the same base? So I call this type 2. Type 2. And we use this when type 1 fails. Okay, so what's an example of an exponential equation where I can't make the same base on both sides? Here's an example. 2 to the, let's say 3x, I'll keep the same as before. Instead of writing 16, maybe I write 15. Okay, so this is not a power of 2, right? 15 is 5 times 3. That's its prime decomposition, which is not a power of 2. What do I do here? Okay, so type 1 fails. Here is what type 2 is. So the step that you need to take here is you need to take the logarithm of both sides. But you don't just take any old logarithm. You actually need to pay attention to which logarithm you're going to use. What's an example of a logarithm that you're going to use in this equation? Well, again, identify that base. My base here is going to be 2. I want to use the base that has the exponent. Okay? So use the base with the exponent. Okay? So what does that look like? I'm going to take the logarithm, right? My base is 2, so I'm going to take log base 2 of both sides. What does that look like? Log base 2 of 2 to the 3x is equal to log base 2 of 15. Okay? So that's exactly what we need to do here. Take log base 2 of both sides, and then we can solve for x. So how does this simplify? Well, there's a couple ways you can look at this, right? The first way is we can rewrite this equation that is how it is now using our properties of logarithms. Last video, we talked about how power rule for logarithms states that I can actually, so essentially I can use the power rule here on this logarithm. And that's important, right? What it says is that I can take the exponent and just bring it outside and multiply whatever's on underneath that. So this is equivalent to using our properties of logarithms, 3x times log base 2 of 2. And that's going to be equal to log base 2 of 15. Okay, so I haven't changed the right side, but the left side I've changed using the power rule. These are our equivalents, so that's totally fine. All right, so we have 3x times log base 2 of 2. Okay, so what is log base 2 of 2? 2 raised to something has to equal 2. Well, that's just 1. So log base 2 of 2, I can actually just cancel out because 3x times 1 is just 3x. Anything times 1 is equal to 1 itself. So 3x is going to equal log base 2 of 15. And as we can see, x is nicely by itself, about to be by itself. I just have to divide by 3 on both sides. X is equal to, oh wow, that's a weird log. Log base 2 of 15. That's another weird 15. Log base 2 of 15 over 3. And there we go. So that's going to be the solution to x. Again, and you can actually get a more concrete answer here by simplifying the logarithm. And again, you need to use a calculator in this case. And again, the way you use your calculator here is you're going to set up this logarithm using the change of base formula, which states that if I have log base 2 of 15, well, this is equivalent to log of 15, or the common log base 10, divided by log of 2, or that base, and that's all over 3. So in your calculator, you're going to plug in log of 15, then divide it by log of 2, hit equals, whatever that equals, keep it the same. Literally don't clear it, don't move anything, and then just hit divided by 3, and that'll give you your solution. And of course, it's going to be like an irrational number. It's not going to be a whole number. Usually it's not. I mean, that's why we're using our calculator in the first place. And yeah, so that's how you plug it into your calculator. All right, now what happens when type 2 fails? When this method fails? Well, it's only going to fail if, so we're going to call this type 3. Whoa, I don't want to use red. So type 3. Again, this is when type, so again, you kind of, the reason why I named it this way is because you want to start with type 1. Is type 1 going to work? Well, no, it's not. Okay, how about type 2? No, it's not going to work. So here's an example of when type 2 fails. Okay. So not only is it going to have different bases, so the way to fail type 1 is if the exponents have different bases. Type 2 states that, right, if I have different bases, it's just the opposition of type 1. Now, when type 2 fails is when not only do I have different bases, but I have exponents in both my on both sides of the equation. So what's an example of that? Well, if we have 4 to the x plus 3 is equal to 5 to the minus x. All right, so here's an example where not only do the bases are not in common, but there's exponents on both sides. All right, so if I took log base 4 of both sides, then kind of end up with something that's not super nice. So what do I do here? Well, type 3 is when I'm going to be taking log base 10 on both sides. So I take the common log of both sides. And so what does that end up becoming? So we have log of 4 to the x plus 3 is equal to log of 5 to the minus x. So I've just taken the common log of both sides. Now I'm going to apply the power rule on both sides so I can get that exponent down and solve for my logarithms and solve for x. So I'm going to take my exponents and just bring them outside. Multiply the logarithm by that, and we end up with x plus 3 times log of 4, and that's going to equal to minus x times log of 5. Bam. So I have x getting closer. So basically what I'm trying to do is trying to get x together and then get the logs on the other side. All right. So how does this simplify? Well, I had this logarithm here. Log of 4. Distribute that to 3 and to x. What does that simplify to? X times log of 4. So I'm just distributing that log of 4 on both sides. Over the parentheses. Plus 3 times log of 4. And then I have this minus x log of 5 over here. And then if we look, I have an x log here, and then I also have an x log over here. I'm going to bring those together, and then I'm going to get my other log, this one, on the other side. Let's see what that simplifies to. So I'm going to take this log, bring it over here, and then I'm going to take this log and bring it over here. So we have log of x, or x times log of 4, plus x log of 5, and that's going to equal to minus 3 log of 4. Okay, so now what I'm going to do is I'm going to use the distributive property to factor the left side of the equation. I can factor out the x like this. Log of 4 plus log of 5, and that's going to equal to minus 3 log of 4. There we go. Okay, so properties of logarithms. Again, I could take a step here that I don't need to do, but I'm just going to do because it's going to simplify my my equation. Is because I'm adding two logarithms here, I can actually just multiply what's on the inside. So this becomes x log of 20, or 5 times 4, and that's going to equal to minus 3 log of 4. And then last but not least, just divide your log of 20 on both sides. So x equals minus 3 log of 4 divided by log of 20. And there we go. Cool thing about this method is that you have only logs. You only have common logs. So at the end, when you solve for x, you can already plug it into your calculator however it is, and that is going to be fine because we have a logarithm function button on our calculator. So that's perfect.